Today we're looking at lesson 6.2, Is It Right? And our objective today is given a line on a graph, I can write an equation for a parallel line and a perpendicular line in 2 out of 2 problems. So we've looked a little bit more at parallel lines than perpendicular lines. We're going to take a closer look today at perpendicular lines. All right, so take a second, remind yourself, what do we know about parallel lines? What are some things we know? Well, we know that they have the same slope, and they have different y-intercepts. We know that they never meet. We know that if it's a system with parallel lines, there's no solution because they never meet, they never cross, and where they cross is where the solution is. What else do we know about parallel lines? Can you think of anything? This is a pretty good list. Maybe let's go over to the other side. What do we know about perpendicular lines? This might not be as much. We might still be figuring stuff out about perpendicular lines. Well, we know that they do meet exactly once. And they meet at a 90-degree angle. We also call this a right angle. That's how we define a perpendicular intersection, or two perpendicular lines, is that they meet at a 90-degree angle. So that's just based on the definition. Is there anything else we know about perpendicular lines at this point? They're not parallel for sure, right? Two lines can be either parallel or perpendicular, but not both. Or they could be neither. But we don't actually know about the slopes of perpendicular lines yet. So maybe let's see if we can figure anything out about that. Before we jump into that, let's look at some notation. A line is identified by 2 points on it. So here, if you look over at this graph, we have an A and a B and a line that runs through it. This is a line that's extending in both directions. If it were only the piece in between it, it would be called a line segment, but since it's the line that runs forever, we call it a line. And we identify this line AB by writing the 2 points that are on it, AB, with a line with arrows over the top. If we were just looking at the line segment, it would be without arrows. And we can identify other lines as well this way. We could do line CD the same way. We could look at line AE the same way. And then we have notation for parallel lines. Do you see any parallel lines on this graph? Yeah, it looks like AB and CD are parallel lines. We said that they will have the same slope, so we can even check that. This goes up 1, 2 over 1, 2, 3. So our slope there is rise 2, run 3. And on CD we go up 2 over 1, 2, 3. So it's the same. The slope is 2/3 on both of those, so we can see they're parallel. And we write parallel lines with this symbol here, which is 2 vertical lines. That kind of makes sense because those are in fact parallel lines. And a way you can type this is using the pipe key on your keyboard. Now that key is usually right above the enter key, and it shares that key with a backslash. Or actually, yeah, that's a backslash. And you will need to use the shift key to type it. So shift and then that button above the enter key, and you should get those little vertical lines. So we could type this as AB, 2 pipes. AB is parallel to CD. And You usually can't type these little arrows, but I sort of understand they're there if you want to type them in chat that way. Now, perpendicular lines. Can you see any perpendicular lines on this graph? This angle right here is marked as 90 degrees, so we know these two lines are perpendicular. So we'd say line AB is perpendicular to line AE. And our symbol for perpendicular is this upside down T. And again, that makes a lot of sense because these are perpendicular lines, right? They look perpendicular, that make a 90 degree. So we would say line AB is perpendicular to line AE. This line is perpendicular to this line. And once again, you can't type, well, you can type that on your keyboard, but it's difficult to do. Perhaps the best way to do this is to use the underscore, which is up near your numbers. You'll need to press Shift, and it shares a key with a hyphen, so Shift and then underscore, and then type a pipe. And if you type it that way, it will look pretty close to that perpendicular symbol. So that's some notation that will be useful for us in this lesson. So let's take a look at a little complicated example here. This big, massive graph with a bunch of messy lines. Can you tell me, can you spot any parallel lines on this graph? And how do you know? How do you know whether they're parallel? Well, maybe you spotted AB. And that looks pretty parallel to IG, line IG. And the way we would determine if they are actually parallel is by finding the slope, finding the rise over the run. So we can come to any intersection and go up 1 over 1, 2, 3, up 1 over 1, 2, 3. So there I just identified that we had an intersection there. And when I say an intersection, I mean at whole numbers on the graph. And to get from one point to the other, we go up 1 over 1, 2, 3, up 1 over 1, 2, 3, and so on. So this is a slope of rise 1, run 3. And similarly, on this line down here, we go up 1 over 1, 2, 3, up 1 over 1, 2, 3. This one also has a slope of 1/3. Can you spot any other parallel lines? Maybe CB and DG. Maybe those ones look parallel. Should we figure it out? So we need points where they cross. It looks like it crosses there. There's one there, there's one here, there's one here. So this goes down 1 over 2, down 1 over 2, down 1 over 2, and so on. So our slope there is rise of -2 over, did that wrong. Rise of -1 and run of 2, right? We went down 1 over 2. Rise of -1, run of 2. -1, 2. So let's check that on this other line. Here's a dot, here's a dot, here's a dot. We go down 1 over 2, down 1 over 2, down 1 over 2, and we get that same slope. -1 over 2. -1/2 is our slope of these lines. Do you see any other parallel lines here? What about EF? Does EF have any parallel lines? Let's look at some points here. There's a point, there's a point, there's a point. Down 1 over 2, down 1 over 2, down 1 over 2. This one looks like it has a slope of down 1, run of 2. That actually matches the ones we've highlighted green. So all three of these lines are parallel. Same slope, different y-intercepts. They all cross at different places, cross the y-axis at different places, but they all have the same slope. So this blue line, this green line, and this green line are all parallel. Now what about these two lines? That one and this one. Are those lines parallel? Let's see if we can find a slope on these. This one's a little bit weird. It takes a minute for it to cross. Let's see, it looks like it crosses right here. And maybe not again until right here. This goes up 1, 2, 3, 4, 5, 6, 7, and over 1, 2, 3. Yeah, that's not reducible. So our slope there is 7/3. Now we'll look at this line in contrast. Let's see, looks like it crosses right there, right there, right here. So this goes up 2/1, up 2/1. This slope is 2/1. So these are very close. 7 divided by 3 is going to be 2.333. This is going to be 2.0. So they're very similar, but they're not quite parallel. They will eventually cross. So it's a very complicated diagram, but we got it analyzed. What about perpendicular lines, though? Can we tell on this graph what lines are perpendicular? How might we be able to tell? It sort of looks like, let's see, let's grab my highlighter here. It sort of looks like this line, BO and BI. It looks like those might be perpendicular. Question mark though. Do we know for certain that it is perpendicular just because it looks perpendicular? How would you feel if the person framing your house was like, it looks perpendicular, it's probably fine. It's probably 90 degrees. It would be best to know for certain to demonstrate that it's actually 90 degrees. Now we could pull out a protractor, which is a tool for measuring angle. That's one way we can determine it's 90 degrees. But we're looking for sort of a constructed geometric way to find perpendicular lines, not just measure them. We want to construct a perpendicular line, not just measure one that's already there. So we actually don't know yet. We don't know for certain which of these lines are perpendicular. We're going to try to figure that out today. We're going to figure out a sort of reliable way to make perpendicular lines. So a good way to do this in geometry is we're going to start out with some simpler lines or a simpler diagram that demonstrates a concept that will be useful to us. And those simpler lines are the x and the y-axis. X-axis, y-axis, and I have this claim here. The x-axis and the y-axis are perpendicular. Do you think that is true? These are perpendicular lines. Now we sort of take that for granted, right? We sort of were told that at one point, and we just believe it forever. That's supposed to be 90 degrees. But is there a way we can know that for sure? That the x-axis and the y-axis were actually constructed to be 90 degrees. Well, let's think about a circle. If we drew a circle around the origin, we know that we're doing an angle all the way around the circle. So basically from the x-axis all the way back to the x-axis. And the way we've defined the x and the y-axis is so that it will create 4 equal quadrants. That means we're going the same amount of angles here, same amount here, same amount here, same amount here. So if we ask ourselves how many degrees are in a full circle, how many degrees do you remember? Actually says right here on the slide. There are 360 degrees in a circle. And if we're dividing it into 4 even quantities, that means we're going to divide it by 4. 360 divided by 4, that will in fact be 90 degrees. So another way to think of a right angle is a quarter of a circle. 90 degrees is a quarter of a circle, or dividing the coordinate grid into quadrants. So we can actually use the same reasoning if we drew a circle, kind of drew a circle freehand here. That's kind of like a circle. If we drew a circle around the intersection between any vertical and horizontal line, we'd have the same argument. These are all 90-degree angles because we're dividing horizontal lines and vertical lines divide circles into 4 even quadrants. So any horizontal and vertical line are perpendicular to each other. All right, so that is our first tool in this construction. But we're trying to figure out how to make a perpendicular line to a diagonal line. Something like that. Is that the perpendicular line? Or is it closer to that? Or maybe it's something more like that. Which one of those lines would be perpendicular? How can we know? Well, we're going to use the fact that horizontal and vertical lines are perpendicular to figure that out. So we're going to start with this example diagonal line right here, this line from A to B. A is at 0.23, B is at 0.47. And our first question is, what is the slope of AB? This is rise over run. So the slope is up 2 over 1. There's a dot right there, up 2 over 1. So our slope is 2 over 1, which we would reduce to 2. Now where could we put a new point, point C, to make this a right triangle? Remember, a right triangle has a right angle in it. A right angle is 90 degrees. So we need to have one right angle in here. So maybe a good place to do that would be on this coordinate grid where A is at the same y value and B is at the same x value. So the place on this coordinate grid where these 2 points would meet at a right angle. Right there. And how do we know that's a right angle? Let's see, where do we put that point first of all? That was at 4, 3. How do we know it's a right angle? Well, we just said on that previous slide, let's see, all horizontal lines are perpendicular to vertical lines. And we know that this is a horizontal line. This is y equals 3. That's a horizontal line. And this is a vertical line. This is x equals 4. That is the format of a vertical line. That's the format of a horizontal line. So we know it's a right angle because horizontal lines are perpendicular to vertical lines. So our next step is to rotate this triangle 90 degrees counterclockwise about point A. So we're going to use our rotations transformation. Remember, a rotation is rigid. The triangle stays the exact same size and shape. It just moves around the plane. So we're going to take this triangle and rotate it around point A here. So it's going to go 90 degrees up this way. So remember, we keep the same distance from the rotation point. So C is 1, 2 away from A. It's going to rotate 90 degrees and it's going to end up 2 points away from A up here. 1, 2. So this would be C prime. Remember, prime is what our image is called. A and A prime are the same point because we're rotating around the A. And then the last question is, where does B end up? B is going to be rotating 90 degrees kind of over here somewhere. Well, we know that this is rigid, right? So we know this distance has to be the same from B to C. So it's 1, 2, 3, 4 right now. It's vertical, so it's going to go horizontal when it rotates. So then it'll be 1, 2, 3, 4 horizontal over here. This will be B prime. Try to draw a straight line here. This is kind of straight from B to C, and then from A prime to B prime. So you can see this triangle is the same size and shape as this triangle. It's just rotated around that point A. It's rotated 90 degrees counterclockwise. And how do we know that it's a 90-degree rotation? It's asking down here. Well, AC and A prime C prime form a right angle. Those are vertical and horizontal lines. So we're just going to keep using the same justification over and over again. Horizontal is perpendicular to vertical. So we know that this rotated 90 degrees because it created a vertical line from a horizontal line. Okay, so we constructed a triangle. We constructed a rotation of that triangle. But here is the really key part. We know two things here. We know that all parts of the triangle were rotated the same amount. That's how we define rotations, right? Every point along that triangle was rotated 90 degrees because C and C prime, you can see this point right there was rotated 90 degrees. So if every point is rotated the same amount, and C was rotated 90 degrees, what would we conclude about B? How much was B rotated? B was also rotated 90 degrees because all points were rotated the same amount. But look at this. If I erase this down here, the angle between B and B prime, the angle made here, is going to be 90 degrees. That's what we just said. It rotated 90 degrees. That created a perpendicular line to our diagonal. That constructed the line we were looking for. So we had this diagonal originally. We have this new diagonal line that is perpendicular to the original one. So we did it. We constructed a perpendicular line. We know that AB is perpendicular to A prime B prime. So now that we know that, we can maybe see if there's a pattern with the slopes. So we already looked at the slope of AB. We said that's rise of 2, run of 1, rise of 2, run of 1. So we said the slope is 2 over 1, which we reduced to 2. What is the slope of this new diagonal line we created? Can you look at that and see? See, we start here, we go down 1 over 2, down 1 over 2, so that sounds like negative 1 over 2. Do you notice anything similar or interesting about those two slopes? Well, 2 over 1 and 1 over 2, they kind of look like they're upside down from each other. And they maybe look like one is positive and one is negative. Those are the things I noticed. Do you notice anything else? So maybe that might give us a pattern. Maybe the slopes of perpendicular lines are upside down and then one is positive and one is negative. Let me think about that. And let's record our slopes for these. We did original slope was 2 over 1, which is the same thing as 2. Our perpendicular slope was negative 1/2. So we said the relationship was they're upside down, possibly, and one positive, one negative. Now we'd want to verify this, right? That's why we have several examples here. And we're just going to do that one example today. We're going to save the other 3 examples for tomorrow and see if we can confirm we get the same pattern. Upside down, which we also call a reciprocal of a fraction, and then one is positive and one is negative. So that concludes today's objective. Given a line on a graph, I can write an equation for a parallel line and a perpendicular line in 2 out of 2 problems. We haven't quite covered all of that yet, so we're just constructing that. We're going to finish this off in tomorrow's lesson.